This is part 2 of the lectures on system properties from Z-transform. In this part, the learning objectives are how to understand the system stability from or by looking at its transfer function, and also I will end by giving an example on an LTI system. Let us first remember together what we mean by a system being stable. So the intuitive definition is that a system is stable if for every bounded input the output is bounded, meaning that the output cannot go to infinity if the input does not go to the infinity. Now, in terms of how we can transform this into a mathematical condition, so I hope you remember this property that a system, an LTI system with impulse response h of n is stable if and only if it satisfies the following property: that the sum of the absolute value of h of k is bounded. So I think here there's no n, so I'm gonna fix it later. And this property is usually referred to as the impulse response of the system is absolutely summable. And to test whether a system is stable or not by looking at its Z-transform, we can do this by checking the following property that says that an LTI system is stable if and only if the ROC and its transfer function h of z contains the unit circle determined by the norm of z equal to 1. So all we have to do is to check whether the ROC contains the unit circle. If it does, then the system is stable. Let us do a quick example. So consider the system with the following impulse response: h of n equal half to the power n plus 2 to the n u of n. Now to check whether it's stable or not, we find its Z-transform. And its the Z-transform of the first part here is 1 divided by 1 minus half z minus 1. And the Z-transform of the second part here is 1 divided by 1 minus 2 to z minus 1. And the ROC is the norm of z greater than 2 because it's a right-sided signal, and there are two poles here, pole 1/2 and pole 2. So if you just want a quick reminder of how we find this, so again, so we have two poles, a pole at 1/2 and a pole at 2, and since the signal the function is rational and the signal is right-sided, so it's gonna be the ROC is gonna be outside of the circle at the outermost pole. And now you can easily check then that the system is not stable because it does not contain the unit circle. So let me draw here the unit circle so we're all at the same page. So it doesn't contain, this is the unit circle. Now let us consider the same system, meaning the same h of z, which we just saw before, but let's change its ROC to be the ROC being this one here. The norm of z is between 1/2 and 2, so let me draw it on this side here. And the ROC is this part here. So it's between the two circles, and now you know that the signal is double-sided in this case. Now it does contain the unit circle. The ROC does contain the unit circle, so this means that the system is stable, and this is what it's saying here. However, if we go back to the previous lecture and ask whether the system is causal, you can see that the system is not causal because it's not the exterior of a circle. So this is an example of a system that can be causal, but that can be non-causal or anti-causal, but stable. Now, if the question is to find the inverse of this signal or the impulse response of this signal or this system, again, it's the same h of z as before. So I think it was, let me write it down. So here, so the question now is h of z is equal 1 divided 1 minus 1 half z minus 1 plus 1 minus 2 to the n, so 2 z minus 1, because there are two poles as, yeah, and then, but here the ROC is this one here. Now you can tell that because it's a double-sided signal, you can see from the ROC here that the part that has 2 as a pole is actually left-sided because it's the interior of a signal. So this is why you have to use the left-sided formula for the pole 2. So this is why we have this part here, because the signal is left-sided. This part is left-sided, again because it's the interior of the circle at 2, whereas the part with pole 1 half, this guy here, is left-sided, and this is why this is the signal. And you can see why here that the system is anti-causal, because it has a positive component for negative time, which are this part here. Now for that example, if you just want to study the last case when the ROC is given by z less than 1, so again I had two poles, one at 1 half and one at 1, and now I'm looking at the case where the ROC is the interior of this circle. This means that both parts of the signal that we did before when you do the partial fraction expansion, both parts are left-sided, and this is why you get the formula here, right? So and then in this case the system is not causal because it has negative components, as you can see here. But also, if you want to see it at the ROC, it's not the exterior of a circle. If you remember, for causality we need two conditions to be verified. First, the ROC is the exterior of a circle going to infinity, and then and also if it's a rational function, the degree of the numerator in z should be less or equal than the degree of our numerator in z. And the system here, so it's not causal and it's also not stable because the unit circle is not contained by the ROC. It's actually outside the ROC. Oh, sorry, I just realized that I made the typo here. So this is the pole here is 2 and not 1. So this covers kind of the three cases, three possible cases for that transfer function. So you had the case where the impulse response is left-sided, or it's left-sided or double-sided, and for each case we studied whether the system is stable or not, and whether it is causal or not. This brings us to a useful criteria for determining whether a system, an LTI system, is causal and stable. And from the previous discussion we can see or say that a system is causal and stable if all its pole or all the poles of h of z lie inside the unit circle, meaning they all must have a magnitude less than 1. So let's do another example. So here consider the LTI system given by the following linear constant coefficient difference equation. So we've done these kind of examples before, and the question is to find the transfer function of this system and discuss causality and stability. So starting from the linear difference equation, once you take the z transform of both sides, the z transform of y of n is y of z, the z transform of 1 half yn minus 1, so this is a shifted version of y of n, so it's going to be half z minus 1 to account for the shift y of z, and then x of z plus 1/3 z minus 1 x of z. And then you get the z transfer of the z transform of the impulse response, which is the transfer function, which is 1 plus 1/3 z minus 1 divided by 1 minus 1/2 z minus 1. Now, what remains to be discussed is the different possible ROCs and then their implications on causality and stability. Now we see that the transfer function has a single pole at z equal to 1/2. So if I want to draw the plots, the zero pole plot, so I would have here 1/2. And then if h of n is right-sided, I know I'm gonna be outside this circle, the ROC. And if the h of n is left-sided, then the ROC is the interior of this circle. So let's do each one of these cases separately. So let's suppose that we are in the first case, meaning h of n is right-sided and the ROC is the exterior of the circle with radius 1/2 and the circle being at the origin. Then in this case, h of z, we can write it. So in terms of causality, we already have the first condition that is satisfied, so it's the exterior of his circle. Now we need to check, since our transfer function is rational, we need to check the degrees of the numerator and the denominator. So here the numerator and the denominator have the same degrees, so the system is causal. And if you look at the unit circle, so the unit circle is inside the ROC, therefore the system is stable. So in this case, the system is stable and causal. So to summarize what we did so far, so we have, this is the ROC here. It's the exterior of the circle here. And the exterior contains the unit circle, which means that the system is stable. And since the ROC is the exterior of a circle and the degree of the numerator is less or equal than the degree of the numerator, therefore it is also causal. Also, we could have immediately deduced this by looking at the poles and seeing that we only have single pole at z equal 1/2 and the magnitude of it is less than 1, so the system is causal and stable, like we saw in the previous properties. So again, you could check if a system is causal and stable at once by checking if all the poles have magnitude less than 1. Now to double check what our conclusion, and also maybe to review how we find the inverse Z transform. So if we try to find the impulse response h of n, meaning we have to invert the Z transform here, we have to invert h of z. So we know that the inverse of 1 by 1 minus 1/2 z minus 1 is a geometric series with of the form 1 to the n, and the other part is a shifted version of the same geometric series, shifted by 1 time and then multiplied by 1/3 here. And remember that since the ROC is the exterior of z greater than 1/2, then for both these components, both of the signals are going to be right-sided. So that's why I applied the right-sided formula. And you can see again that the system is causal because it doesn't have any negative components, any non-zero, so it's just basically it's 0 for all the negative times. Now the second case is when h of n is left-sided, and this implies that the ROC here is the interior of z equal to, or magnitude of z equal to 1/2. I'm going to draw the ROC here, so it's the interior of this region here. And then if you want to check for stability, it's clear that the unit circle is not in the ROC, so therefore the system is not stable. And now also the system is not causal because the ROC is the interior of a circle. So the system is is anti-causal and is also not stable. And in this case, if you want to check the impulse response, then you do the same thing we did before, but you have to keep in mind that both components of the signal or the inverse transform, the inverse Z transform of the impulse function are left-sided here. So I have minus 1/2 to the power n u minus n minus 1 minus 1/3 1 over 2n minus 1 u minus n. So I have the first signal plus 1/3 a shifted version of it. So for the second case, to summarize, it's neither stable and neither causal.